Hello, welcome to CFD by Hugo Castillo Sanchez. I'm Hugo, and before starting the video, I would like to introduce myself and talk about my academic profile. I would also like to explain the main goal of the channel. But if you want to go directly into the content of the video, I have left timestamps down below. So I'm Hugo. I studied my bachelor's degree in chemical engineering at the National Autonomous University of Mexico. I also studied my master's degree in chemical engineering at the same institution. Then in 2015, I moved to the UK to study my PhD in applied mathematics, where I graduated from University College London, or UCL. I studied there non-Newtonian fluid mechanics, which is non-Newtonian fluids are the fluids that do not behave like standard fluids, such as water. Then in 2021, I moved to Brazil. I was a postdoctoral research associated to the University of Sao Paulo. And in Brazil, I started working with CFD, or Computational Fluid Dynamics. And there, my main job was to implement models for fluids of industrial interest into a CFD software that was being developed by my colleagues in Brazil. My research interests are rheology, which is the science of deformation. I'm also interested in CFD, of course, non-Newtonian fluid mechanics, and in transport phenomena, which is the transfer of physical quantities such as mass, momentum, and energy. I have published over 8 peer-reviewed journals, 8 peer-reviewed papers in international relevant journals, and also I have attended to different international conferences related to my field. So this personal project of mine has different goals. For instance, when I was a student, I noticed that the documentation related to CFD is very limited. Also, for those that have started working directly with CFD simulations, the theory might be a bit complex, especially if you don't have an engineering or a physics background. In addition, although you might have experience using CFD software, most of this software, especially non-open source, work as a black box. So you don't really know how the software works. So not understanding the theory or how the software works might be a limitation to carry out more optimal simulations. Therefore, in this channel, I want to make accessible the theory behind CFD for all kinds of students, from masters to PhD students. Also, it can be useful for even postdoctoral researchers. So I'm aware that there exists already plenty of good channels, good YouTube channels related to CFD that cover different topics such as programming or using a particular CFD software or carrying out a simulation in complex geometry. But in this personal project I'm creating, I want to do it my own way. Most of the CFD channels focus, for instance, on aerodynamics, on turbulence. But here I want to give a perspective from a researcher that is interested in the simulation of complex fluids, for instance, in the simulation of molecules or polymers that are moving, that are flowing. So my plan is to cover the very basics of the theory of CFD as a starting point. So I'm offering a free course of introduction to CFD, where I will cover in the following topics. For instance, I want to talk about what is CFD, how it can be used, what are the prerequisites needed to learn CFD. Then I want to talk also about my research, what I have done related to CFD, what kind of fluids I'm studying, or what kind of fluids I'm interested in. Then I would like to give an introduction to the most common equations used in CFD, such as continuity equation, which is the mass conservation equation, but also the momentum equation, or the Navier-Stokes equations. I also want to solve analytically the Navier-Stokes equations for a very simple fluid like water, for in standard geometries such as simple shear flow and simple shear flow with a pressure gradient. Then I would like to give an introduction to the most common numerical methods used in CFD to solve partial differential equations, which is the finite volume method and the finite difference method. So I also want to talk about my research and focus the channel in CFD related to low inertial flows, which is in contrast to the common CFD YouTube channels that focus, as I said before, on high Reynolds number or in aerodynamics. So if you are a student that is interested in this field, or you want to do a thesis that will use CFD, I highly recommend taking this course I will be offering for free in my channel. On the other hand, if you already have worked on CFD, or you also have already good experience using CFD, but you want to review or relearn some concepts, the individual videos I will be uploading into this channel might be a good option for you. So another goal of the channel is I want to upload content in both Spanish, which is my native language, but also in English. So I want to create one of the very first bilingual channels that focuses on CFD and fluid dynamics. Also, another goal is that I recently finished my postdoctoral position. I'm looking for an assistant professor or tenure track position where I will be very interested in teaching different fluid mechanics courses, CFD courses. So this project is also helping me to practice giving lectures. So any feedback, any suggestion is highly appreciated. So after uploading the content of my course I will be offering for free, which is Introduction to CFD, I'm planning to upload more content related to fluid dynamics, to computational fluid dynamics. So if you have any suggestions, or if you like my videos and you want me to keep uploading content, please give me suggestions in the comments. And yeah, any feedback is appreciated. So thank you for staying here. Thank you for joining the channel. So enjoy the content. Hello, welcome to this presentation called Introduction to Computational Fluid Dynamics, or CFD. I'm Hugo Castillo Sanchez, and this video is part of a course I will be offering for free here in my channel in YouTube. In this very first presentation, I want to explain what is CFD. In other videos I'm planning to upload, I will be focusing on explaining the physical meaning of the most popular equations used in CFD, which are the continuity equation or the mass conservation equation. And also I want to give a brief introduction to the momentum conservation equation, or the Navier-Stokes equations. In other two videos I want to solve analytically the Navier-Stokes equations for two standard geometries used in CFD, which are the simple shear flow and shear flow with pressure gradient. And lastly, in the last two videos of this course, I will give a brief introduction to the most popular numerical methods used in this discipline, which are the finite volume method and the finite difference method. But in this presentation, let's start. Here, I just want to briefly describe the content of this video. Yeah, I want to explain what is CFD, which applications it has, this discipline. Also, I want to give a brief description of the theoretical content needed to learn CFD. I also want to focus on give a brief description of the differential equations and numerical methods used in CFD. I also want to explain or describe some of the most popular software used to simulate flows. And lastly, this will be part of the second video, but yeah, I want to show some of the numerical simulations I have personally carried out using CFD, and yeah, describe my research in this topic in CFD. Well, the impact of fluid dynamics in our world. Fluid dynamics is, in a few words, a branch of mechanics that studies the movement of fluids, for instance, liquids and gases. And fluid dynamics applies to many fields, including engineering, biology, astronomy, among other sciences. And fluid dynamics is not a new science. It has been used for centuries. For instance, the Romans, they used the principles of hydraulics to develop or to build aqueducts, which were used to transport water from one city to another. Also, the Greeks used concepts of fluid dynamics. For instance, Archimedes, he developed his principle that stated or states that the Boyan force on an object is equal to the weight of the fluid displaced by the object. Also, Newton developed developed his law of viscosity, which we will be talking about this law in the upcoming videos. But yeah, fluid dynamics is also nowadays used to study phenomena that are present in our daily life. For instance, it is used in weather forecasting, to study ocean currents, plate tectonics, and blood circulation. I have some colleagues of mine that develop a bracelet that can measure the level of cholesterol in your blood, and they developed this bracelet using principles of fluid dynamics. And yeah, this discipline also has important technological applications in aerodynamics, for instance, for the development of aircrafts, also to develop or to optimize Formula One or F1 cars, and also is used to develop rocket engines, wind turbines, and yeah, fluid dynamics is used also in the chemical industry, particularly in polymer processing and in the oil industry, among other disciplines. And from time to time, the rapid development of science and technology has forced engineers to solve enormous challenges. For instance, problems that were impossible to solve 100 years ago now are easier to handle because our power or computational power has evolved over the last year. So now with more technological resources, we can solve problems quicker, faster. And with such challenges, the engineering projects in all domains are getting more convoluted and more exhausting. Also, our society is evolving. So now we need to find solutions to problems, to new problems. For instance, to study the climate change, also to look for new. We need to look for new renewable resources. And to solve these challenging problems, engineers and experts have always relied on sophisticated tools. And tools like this assist a company or the government or mechanical design firm in tackling a problem with this. And one powerful engineering tool that is widely used nowadays in almost every industry is computational fluid dynamics, or CFD. Well, CFD is basically the analysis of fluid flows using numerical solution methods. And yeah, if you use CFD, you are able to analyze and solve complex problems involving mono and multi-phase problems. This means that you can solve a single phase flow, such as water, but you can also solve multiple phase problems. For instance, you have a mixture of multi-components. You can have water, you can have oil, you can have also water with a polymer. Yeah, multiple things. And fluid dynamics is involved with physical laws in the form of partial differential equations. So so as I was saying, CFD is a engineering tool that is used to solve complex flow problems. So the engineers have developed CFD software that can help us to simulate fluid flows. And these CFD softwares, their job is to transform these laws into these laws, which are usually expressed in partial differential equations. So the CFD solvers are going to transform these partial differential equations into algebraical equations.
and the CFD software are able to efficiently solve these equations numerically. So yeah, I here have this picture that describes some applications of CFD. For instance, CFD can be used in the car design. Here, I just put an example of a car that is interacting with air. So these kind of simulations are useful for to engineers to study drag force, because the car is moving in this direction, but the air is going to move in the opposite direction, and drag is the force that opposes a car motion uh, through air. So yeah, in a car you want to reduce this drag force as much as possible. CFD also has applications in aircraft design, in aerospatial engineering, where you want to efficiently design wings of a plane to reduce also drag. CFD is also used to simulate waterfalls or other geological flows. Also CFD has important applications in biological flows, including blood flow simulation or blood flow circulation. And blood flows through arteries, and arteries can have different surface sizes. And yeah, blood might also have other components such as cholesterol. So the flow of blood is affected by, can be affected also by cholesterol. And in the sports, in the design of sporting clothes, CFD can be also used to reduce, for instance, the force of the resistance of the water to the movement of an athlete. And yeah, CFD is an interdisciplinary subject, which means that you need fundamentals, you need principles from different disciplines. Here I include a very quick simple diagram that shows, for instance, if you are interested in applied mathematics, but also you are interested in computer science, you can use both disciplines to carry out numerical analysis and programming. For instance, machine learning, to develop algorithms of artificial intelligence. Also, if you want to do or you want to study applied mathematics with engineering or biological and physical sciences, well, you can, for instance, study population balance in biology. You can also solve the wave equations or the heat equations. So you formulate the problem, and then you use a numerical technique to solve the equation resulting from your analysis, and then you interpret the results. You get conclusions from solving these equations that have applications in different areas. And also you might combine engineering, biological and physical sciences with computer science, and then you can use for instance, images and large databases to detect patterns. Um, for instance, nowadays computer science and biology can be used to detect cancer of mama. This is just an example. But if you combine these three disciplines, you can carry out modeling and simulation. And CFD is actually belongs to this to the center. And CFD is a combination of the fundamentals of fluid mechanics with numerical methods and with computer science. So yeah, what are the prerequisites needed to learn CFD? Well, of course, you need to know the basics of fluid mechanics. This includes the continuum mechanics. You also need to understand mass, momentum, and energy conservation laws. For instance, yeah, you need to understand a bit of the first law of thermodynamics. You also need to understand a bit of Newton's second law. We will be talking about this in the upcoming video, so don't worry. I want to, in the next video or in the next few videos, I want to focus on mass and momentum conservation laws. So you also need fundamentals of linear algebra. You need a strong background of mathematics. This includes, for linear algebra, you need to learn matrix operations, also tensor algebra, and tensor analysis. You also need to have a good understanding of vector calculus and differential equations, particularly the divergence theorem or the Gauss theorem. Also, you need to be able to solve ordinary and partial differential equations. You also need to be able to solve these partial or ordinary differential equations using numerical methods. For instance, Runge-Kutta, your Euler methods. Yeah, all those methods that you learned in your differential equations courses. And more, I consider this very important, that you need good coding skills, and you need at least to learn one programming languages, and the most popular ones are for CFD, particularly C, C++, or Python. And yeah, so what are the most common conservation equations used in CFD? Well, in order to simulate a fluid, you need at least these two equations. Here in the first one, you need the continuity equation or the mass conservation equation, which basically tells you that the mass is conserved in your geometry where you are simulating your fluid. Yeah, I will be talking about this, the physical meaning of this equation in the next video, so don't worry, you don't have a background on this equation. Also, you need the momentum conservation equation, which basically, if you haven't taken courses of fluid dynamics before, this momentum conservation equation for fluids is basically Newton's second law of movement. So here on the left, you have acceleration. If you remember, Newton's second law tells you that acceleration of a body is caused by external forces acting on the body. For fluids, it's similar. So you have an acceleration. Momentum is defined as the density multiplied by the velocity. So the momentum is going to change on a fluid if external forces are acting on the fluid. So this is just an acceleration. So we have a temporal derivative, which is related to a spatial. No, temporal acceleration. If you remember your physics lectures, acceleration can be seen as the rate of change of the velocity with respect to time. So yeah, here we have an acceleration. Here we also have an acceleration, but it is an spatial acceleration, which tells you how the velocity is going to change in the direction of the flow. So I will be talking about these concepts also in a different video, so don't worry, you don't know about them. So these accelerations can only be caused by the action of forces. Here we have the gradient pressure, which basically tells you that there might be a pump that is displacing the fluid from let's say from the bottom to the top in a house, for instance. This S is a source. This term is called as the source term, which means that gravitational effects or an electromagnetic force is affecting the movement of the fluid. So yeah, this is called as the source term. This term in the middle is called the internal forces or the diffusion forces. So here sigma is
Equation 2 is a general equation that can represent every fluid in the world. But every fluid behaves differently. That means that the way that water behaves on the flow is not going to be the same, for instance, for chocolate or paint or volcanic lava. So every fluid in the world will behave differently. So we need an equation that can tell you how the fluid is going to behave when it's moving, when it's flowing. So this sigma is known as the constitutive equation, which is specific for every fluid that you want to study. So yeah, it is also known as the stress tensor, which are the internal forces that a fluid experiences when the fluid is moving. So yeah, this is what I was saying, that for each fluid in the planet there exists a sigma or a constitutive equation that describes how the fluid will behave on the flow. And yeah, here U is the velocity, T is the time, rho is the fluid density, P is the pressure, and yeah, so at least you need these two equations to simulate a fluid, but you might need additional equations depending on your goal. For instance, if you are simulating a fluid and the temperature is changing, you might need energy conservation equation. So you need an equation that can model how the temperature changes with respect position and with respect time. And also, if you are modeling a gas, you might need an equation, a thermodynamic equation, an equation of a state. For instance, if you know thermodynamics, you might need a Penck-Robinson van der Waals equation. So these equations are going to give you the pressure as a function of the volume and temperature. And yeah, as I was saying, you might need a constitutive equation that relates the stress tensor, the internal forces, with the gradient of velocity. Normally, for a constitutive equation, they are usually dependent on the gradient of velocity. I will be talking about a bit also in the next videos. So in my field, the field I studied, the field I have studied over the last years, I usually work with this equation, constitutive equations. I have worked with polymers, I have worked with micellar solutions or surfactant solutions. I have worked with elastoviscoplastic materials, which are used to describe mods, cements. So every single of those fluids need a different constitutive equation. So if you are interested in my work specifically for those kind of fluids, I recommend you to see my next video. Not this one, the next one, the one that will be uploaded after this video. So numerical methods using CFD. So as I was saying, physical laws such as mass conservation or momentum conservation that govern the behavior of fluids are expressed in partial differential equations. These equations might look simple, but they are actually represented in vector notation, which means that this equation is actually a system of three partial differential equations. If you are in Cartesian coordinates, you need an equation for the velocity in x direction, you need another one for the velocity in y direction, and you need a third one for the velocity in z direction. So yeah, you can see why simulating a fluid can become challenging and complex, because you need to simulate three partial differential equations which are non-linear plus a mass conservation equation. And if you are simulating a non-isothermal flow or a gas, the problem becomes really complex. But using numerical methods, you might simplify the problem, because CFD solvers transform these laws, these partial differential equations, into simple
algebraical equations. And this process in CFD is known as discretization. And the most popular discretization techniques are the most popular one overall is the finite volume method. I will upload a video focusing. I will be talking particularly about the finite volume method and how it is used in CFD. Because it's the technique most popular. If you want to study CFD, you want to simulate a flow, this is the technique that you will be using almost always. But there are other techniques that that can be used to solve these differential equations, and one of them is the finite element method, which is usually most popular in the simulation of solids, but it can also be used in the simulation of fluids. And you also have the option to use the finite difference method. I will also be talking about this technique in another video. In my postdoctoral project, I was working with a software, a CFD software that used this technique. So if you are interested, I will be talking about this in a few minutes. And once that you have carried out the discretization process, or you have discretized the equations, that means that you have transformed these partial differential equations into algebraical equations. You will assemble those algebraical equations into simple matrix linear system, which will take the following form, where A is the matrix of coefficients, B is a vector of constants, and U is the vector of variables. So this variable, this vector U, can be velocity, it can be temperature, it can be concentration. It really depends on the problem you are solving. But this is a simple matrix system which can be solved using some of the techniques that you have learned in your courses, in your linear algebra courses, such as the Gauss-Jordan. There are multiple techniques to solve this system. But don't worry, all the CFD software will populate the matrices automatically for you, and also the CFD software will solve the matrix system for you to find U for a given time t. So CFD softwares. The CFD analysis is usually composed of three major steps. The first one consists of the pre-processing step, where basically, let's say you want to simulate a fluid flowing through a channel. Okay, so you need to solve those differential equations in a channel, let's say a rectangle which has length L and width D and height H, for instance. So you need to specify that geometry, you need to create that geometry, and also you need to do this step, which is called meshing. That meshing consists of, for instance, this is your channel, you will split your domain into smaller cells. So you will need to solve the conservation equations, the partial differential equations in each cell. So this is called meshing. This process is called meshing, that you split your domain in very, very small cells. And then the next step is called simulation, which consists of solver setting and numerical simulation. This basically means that in a CFD software, you will specify the numerical techniques that you need, that you want to use to solve the system of equations. For instance, Euler numerical techniques, Runge-Kutta, all those solvers. Also, you specify the parameters that you want to, under which conditions you want to simulate your flow. For instance, you specify that your fluid is isothermal, that means constant temperature. You also specify the, let's say, the values of the physical constants, the physical properties, for instance, the density, you might also have to specify the viscosity. So all that kind of information is specified here in solver setting. And also the next step is numerical simulation. So the software, once that you have specified all that information, the software is going to solve the linear matrix for you. So yeah, this simulation step also, the CFD software is going to transform those laws into this matrix system, and simulation consists of solving this system. And lastly, the post-processing step. Okay, so the CFD solver is going to solve the equations for you, but now that you have the solution, which conclusions you can get from those results. So yeah, so here in this step you will interpret those results in a physical meaning. So also this numerical data can be expressed in images in order to understand what's going on your simulation. So yeah, post-processing consists of the analysis of results from your CFD data obtained from the simulation. So many CFD softwares, both commercial and open source, are available. Some examples of commercial softwares, which are usually more user-friendly, are ANSYS Fluent, COMSOL, StarCCM. Yeah, these softwares are common in the industry. The disadvantage of these softwares is that they are usually a black box. That means that you cannot get access to the source files. So that means that you cannot see how the solvers from these softwares are solving the equations. So you don't get access to that kind of information. In contrast, the open source softwares let you do that. So that means that you can get access to the source codes. You can see all that kind of information that the software is using. You can also modify them according to your needs. You can implement new stuff. Yeah, among many other things. So the most common examples of open source softwares are OpenFOAM, which is actually the most popular software out there. It's written in C++. You also have the ReoTool software, which is based on OpenFOAM, but ReoTool is designed or was developed to solve complex fluid problems. And FOAMXN, which is a OpenFOAM sister system. FOAMXN is much more optimized than OpenFOAM. So yeah, OpenFOAM software is the leading free open source software for CFD. As I was saying, it's a program, software written in C++, and it's a toolbox for the development of customized numerical solvers and pre- and post-processing utilities for the solution of continuum mechanics problems. That means that OpenFOAM is not limited to solve only fluids. You can also simulate solids or other deformable objects. And OpenFOAM is really popular because it consists of a large base library. You can carry out multiple tensor operations. There are multiple techniques of discretization available for the solution of partial differential equations. OpenFOAM also has multiple linear system solvers, general physical models. You can simulate either a gas or a liquid. You can also incorporate chemical reactions to your simulations in case you are simulating, for instance, a reactor. You can also simulate non-isothermal flows. You can incorporate heat transfer. Turbulence, this is also one of the most modern popular topics nowadays in fluid mechanics. Turbulence is the chaotic flow of fluids at high speeds. And yeah, and turbulence is seen in the industry a lot, so that's why it is important to study or to model this phenomenon. And in OpenFOAM, you can also simulate complex fluids. That means fluids that are not the standard like water. And OpenFOAM is based on the traditional finite volume method approach to discretize and solve the partial differential equations. As I was saying, you are interested in doing CFD, in studying CFD, and you will be working in the academia, it is likely that you will be using OpenFOAM, and that means that you will be using the finite volume method. So that is why it is important to understand this numerical technique that I will be talking about at the end of this course, and in one of the videos I will be uploading in the future. I also want to talk about this software I was working with. So I was a postdoctoral researcher in Brazil, working. I was a postdoctoral research associate at the Institute of Mathematics and Computational Science from the University of Sao Paulo. So in this project, I was part of a group that was developing a CFD software called HiGFlow. HiG stands for hierarchical grids. I will be talking about a bit about hierarchical grids in a minute. So this software, HiGFlow, is written in C language, and it is used to simulate single and multi-phase flows of both Newtonian and non-Newtonian fluids in hierarchical grids. Newtonian fluids are fluids like water. Non-Newtonian fluids are fluids that are not water. If you are interested in my research, in my work, I was working with this kind of materials, which are materials that have applications in the industry. And yeah, this system was able to simulate this kind of fluids in hierarchical grids using a numerical method based on the finite difference technique. So this is in contrast to OpenFOAM. OpenFOAM, as I was saying, is based on the finite volume method, but HiGFlow uses finite differences. So I will also upload a video talking about the finite difference technique if you are interested. So this finite difference method was developed to solve partial differential equations that are derived from Newtonian incompressible flows. That means liquids like water. So yeah, that numerical method was published in 2019, and the HiGFlow system, is being developed in a modular way, allowing new techniques and methods to be easily tested and implemented into the system. This is another advantage of the open source softwares, that the software lets you do that. You can modify the files according to your needs, and you can implement new stuff. And the HiGFlow project was funded by, this was my sponsor in Brazil, the Sao Paulo Research Foundation. And the HiGFlow project was also funded by Petrobras, which is one of the largest oil petroleum companies in the world. It is a para-state company. And yeah, in case you are interested in my work using this particular CFD software, I also work with a finite volume method, with the OpenFOAM method, where my job in Brazil was implementing constitutive equations into this software. So once that I implemented those models into this software, I validate my simulations by comparing my results obtained in HiGFlow with results obtained using OpenFOAM, ROTOOL, and FOAMExtend. So you want to see my work, I will include the references at the end of this video. And I will also put a link in the comment section below. If you want a free copy of the papers that were published in international journals, I can hand you a copy for free. You just need to send me an email or write me an email. So yeah, I want to explain a bit about what is a hierarchical grid. A hierarchical grid is a tree-based data structure. So what is that? So let's say we want to simulate the fluid of water in this square. So this square can be called as the root or the father cell. So we can split this cell, the root cell, into 4 smaller squares, and we will have the square 1, the 12, this one, and this one, which are these ones. And we can keep splitting those smaller squares into even smaller squares. For instance, this one, we can have these 4 squares, 13, 14, 15, 16, and then this square, which is this one, we can split it in 4 more. And then the 4 smaller squares can also be split into even more smaller squares, which will be 3, 4, 5, 6. So yeah, this is the concept of a hierarchical grid. We have the cell father, which is the big square. This square can have children, which are these squares, and then the children can have more children, and so on. So this is a computational cell representation that can be used in HiGFlow. And yeah, this is a tree based structure. So why are they useful? These hierarchical grids, how can they be useful in the simulation of flows? So let's say we want to simulate a fluid flowing through this channel. Let's say we want to simulate how water flows from here to here. And as you know, we need to create a mesh. That means we have to split our domain, this rectangle. We have to split it into cells. And the smaller the cells, the more accurate your solution will be, since the numerical solution obtained by the CFD software will be closer to the original system of equations. The problem with using smaller cells is that it can take long simulation time to solve the equations, which can also consume a lot of computational resources. So for instance, as I was saying, every CFD software will create the mesh for you. That means that we'll split the domain into smaller cells, and the CFD software will solve every single conservation equation. That means the mass conservation and momentum conservation equation into each one of these cells. And if the full domain is composed of only small cells, it will take a lot of time to solve those equations in each cell. And this means that it will take a lot of computational resources. So you can also simulate your flow using bigger cells. That means that the mesh can be composed of really big squares. But the disadvantage of doing that is that your numerical solution is not going to be really accurate. So you need to find a balance. So yeah, instead of simulating the mesh with either only small cells or bigger cells, you can use this kind of meshes where the cells with bigger size are used in the center and the smaller cells are used near the walls. And this is important because let's say in most cases the most interesting behavior happens at the walls, because the fluid is going to be in contact with a solid surface, and there might be frictional forces. So the behavior of the fluid is going to be more interesting here, and compared to the center, which is at the center usually the behavior is predictable. We normally know what is going to happen at the center. So if you use bigger cells at the center, you will not compromise the accuracy of the solution. And by using smaller cells close to the wall, you will still have you will still be able to get physically relevant information near the walls. So yeah, this is an example of a hierarchical grid. And you can also opt to use this kind of meshes. This process of using different cell sizes is known as refinement. So you have a refinement near the walls, but you can use meshes with two refinements. You have big cells at the center, slightly smaller cells here, which is the first refinement. The second refinement is very close to the walls, which is where the smaller cells are found. And yeah, another kind of refinement is in this kind of geometry, which is a contraction geometry, which is also used in polymer extrusion. You have a contraction, let's say a polymer is being pushed into a channel with a smaller surface area, and the most interesting behavior is going to happen near the contraction here. So you want to get an accurate solution in this region. So you do a refinement near this region where you use very small cell sizes. Yeah, this is an example of simulation carried out using HiGFlow from my colleagues that was published in 2019, where we have a complex 3D arrangement of channels. So water is flowing through this snake-like geometry. We have two inlets. The water is entering through this area, but is also entering through this inlet, and the water is flowing here, and then it will exit through these two outlets. And this color map scale tells you how the velocity varies along the geometry. So the blue values of velocity means that the velocity is going to be low, but the largest velocity values are seen, for instance, here, and slightly here. So yeah, this simulation was carried out using HiGFlow, which uses finite difference method. So this is the end of the first video. If you are interested in my work, or in case you want to see simulations of using CFD in different CFD software, I recommend you to watch the next video. And thank you for staying here. Thank you for watching this video. If you have any comments, suggestions, please leave them in the comments.